Well, so to continue with our discussions, we had left the discussion in the last class when we were trying to find out Zm in terms of Amagat's law of additive volume, and as I had said in terms of Dalton's law of additive pressure. Now, we had already derived from the Amagat's law of additive volume. What did we get? We expressed Zm in terms of Zi, where the Zi's, all the Zi's has been determined at the T and P of the mixture. Fine. So, therefore, this, as I have said, this is approximate for real gas mixtures and valid for mixture of ideal gases, right. Now, let us take up the other law for finding out the partial pressure. All of us know this is nothing but Dalton's law of additive pressure. What does it say? It tells us that total pressure exerted by an ideal gas mixture, it is nothing but the sum of the partial pressure, or in other words, the pressure of the gas mixture, it is nothing but the pure component pressure. What is this? This is the pure component pressure, which is pressure exerted by Ni moles of pure component gas I if it occupies the entire volume V at temperature of the mixture. So, therefore, T mixture and T pure components are the same, and the partial pressure is nothing, it is simply the pressure exerted by Ni moles of the gas if it occupied the entire volume. Now, under just it is important to remember that for real gas mixtures, it can happen that the pure component pressure, the Pi, this is usually known as the pure component pressure. Okay. This pure component pressure may not be equal to the partial pressure. It can happen if interactions are quite dissimilar, but for ideal gases we always have Pi equals to Pi. Fine. Now, in this case, let us find out Zm prime. I have just written the prime just to differentiate the compressibility factor obtained, mixture compressibility factor obtained from Amagat's law and the mixture compressibility factor obtained from Dalton's law. Now, what is Zm prime equals to? This is nothing but equals to P, the total pressure, V by N RT, which can be written down as V by N RT sigma of Pi, which is nothing but equal to sigma of Ni by N Pi V by Ni RT. Fine. Now, what is this? This is also a form of Z. So, therefore, can I not write it down as Ni by, or else I write it down as Yi, considering that this is a gaseous mixture, into Z I prime. So, therefore, from both the equations, what have we got? If I just write down the other equation here just for comparison, we get Zm is equals to, sorry, this is Yi Z I. Fine. Now, just see the difference between the two. I can predict the mixture compressibility factor either by using the Amagat's law of additive volumes, which I have derived here, or the Dalton's law of partial pressure. We find that from Dalton's law of partial pressure, the mixture compressibility factor is defined in terms of the pure component compressibility factor, where this is taken at system temperature and pure component pressure. This is something very important. So, in this case we express it in system temperature and pure component pressure, or the pressure which this particular gas would have exerted had it occupied the entire volume. While from Amagat's law we express it in terms of the pure component compressibility factors, where these are expressed at system temperature and pressure. So, well, this was one. The other way of finding out Z is, we had already discussed, apart from the cubic equations and the virial equations of state, we had also discussed the compressibility factor charts, where we had shown Z as a function of PR and TR, right. So, therefore, from these equations, suppose there is some particular way of finding out the pseudo critical constants, as it is said. Suppose we can find out the TRM and PRM for the mixture case, then using these two values, since we know that the compressibility factor chart, it is applicable for both for all particular substances. So, therefore, what we can do, we can find out, if we can propose some pseudo critical constants, then in that case, using the compressibility factor chart also, we should be in a position to find out Z. Now, usually there are several again mixing rules for finding out the pseudo critical constants. We find that there is a case rule which gives the mixture, the PCM, the critical pressure of the mixture, and the TCM both as additive function of pure component critical constants, from where the reduced components can be found out, and this particular graph can be used. But usually we find out that although from the TCM value gives quite accurate cases, again in this particular case, since the mixture critical pressure again is a function of the interaction of the different molecules in the mixture. So, naturally the additive equation usually does not hold good, and accordingly another equation has been proposed by Pruschnitz and Gunn. This particular equation, along with the additive law which for the critical mixture critical temperature, these two combined, they give a better result, and so therefore, usually what is recommended is you use this particular TCM, you use this particular PCM, and then you try to use this particular compressibility factor chart for better results. And if you are going for a 3 parameter law of corresponding states, then usually this particular equation is used to find out the mixture acentric factor in terms of the component acentric factors. Now, so with this what I do, I have finished up, or rather I have covered the estimation of properties of real gas mixtures, or for that matter estimation of total properties of any particular mixture in terms of the properties of the pure components. And I have proposed different mixing rules, and I have proposed different combining rules. So, now suppose I would like to predict the fugacity of the component, right. So, for predicting the fugacity of the mixture, this is the equation, right. So, therefore, for other things it is pretty straightforward. If you want to predict H, S, U, A, G, you can do it. Let us take up the fugacity of the mixture. This simply for finding out the fugacity of the mixture, what we need to know the molar volume of the mixture, right. What is the molar volume of the mixture? This Vm, this is nothing but equal to the total volume divided by capital N, the total number of moles of the mixture. It is not at all, it is not very difficult to find out this equation, and from here we can find out the value of Fn, right. But we need to remember what is the purpose of the fugacity. Why did we define fugacity? Fugacity was defined in order to provide a quantitative prediction of phase equilibrium in terms of some physically realizable quantity, right. So, therefore, we had, if you recollect in the while we were discussing fugacity, what did we do? we reframed the entire condition of equilibrium in terms of temperature, pressure and fugacity. What was the condition for fugacity, which refers to chemical equilibrium? If you remember, it was Fi alpha equals to Fi beta, which says that the fugacity of each component I in the different phases should be equal. So, therefore, if we really want to find out whether two phases are in equilibrium, what do we need to calculate? We do not need to calculate Fm. On the contrary, we need to calculate the we need to calculate the fugacity of the individual components in the different phases, right. So, rather than this particular equation, what we would need under that condition is the equation which I have written down here. So, if I have to write down this equation, what do we find? Just for the time being, you just note that this refers to fugacity coefficient of component I in the mixture. This refers to the fugacity of component I in the mixture, right. We will have more discussions, because this is something very special and very different from other molar properties of components in mixtures. So, therefore, for this what do we need? We need to find how the volume of this particular component, the total volume Vi of the component varies with Ni. This particular data we need. Now, what is this data? For pure components, we know, suppose we are dealing with pure components. So, therefore, under that condition, this particular del V del N at constant T p, it is nothing but the molar volume, very easy to find out. But in this particular case, can we simply substitute the molar volume in this particular equation, or will the volume contributed, the contribution of the volume of component I when it is in a mixture be different as compared to the contribution of component I when it is added to its own particular system. What I mean to say, that when I is added in a large amount of I, suppose 1 mole of I is added to a large volume of I, it contributes its molar volume to the mixture. The mixture volume increases by the molar volume of component I. Now, if the same component I mix it or I add to a large volume of say component J, then in this particular case, is it going to contribute its molar volume, or is it going to contribute something different from the molar volume? So, therefore, we discuss all these things regarding the partial molar properties, as they are called, in the next class, and then it will be easy for us to understand how we can predict the fugacities of components in mixtures, and then from them that how we can find out the phase, or rather how we can deal with different phase equilibrium problems.